Hello, everyone, and welcome to Echo Live, coming to you from the Michigan Science Center. Today, we have a very special episode of Echo Live. We are joined again by Raul, who is here to talk to us about sound waves and sound energy. So we've got a pretty exciting day planned. Raul will pop in here in just a moment. Before he does that, we see some people joining in on Facebook and through Zoom. Go ahead and introduce yourself in the chat. That's your best way to communicate with us throughout the program. If you have any questions about sound or questions for Raul, who is a musician himself, you can type those in the chat. Now, I know Raul will also have lots of questions for you all about sound waves and sound energy. If you know the answers to any of these questions, you'll want to type those in the chat as well so that Raul and I can both see those. So Raul, why don't you join on in here? And we can get started in just a moment. I'm seeing lots of familiar faces here in the comments. So hello, everyone. Thank you so much for joining us. I see a lot of friends who join us every day and some new faces as well. So welcome. And hi, Raul. How are you today?
Pretty good, Anna. How you doing?
Great. So we've got some friends joining in the chat. So we've got some friends joining in the chat. I'll keep an eye on those. I'll let you know if we have any great questions in the Facebook chat. But with that, I'll let you take it away. Have fun.
Thanks a lot. All right. Hi, everybody. Thanks for being here with me today. Once again, my name is Raul. I'm an educator at the Michigan Science Center, and I am also a musician. So today, I'm going to be talking to you all about sound. And this is probably something you're already familiar with, right? But my first question to everybody is, what is sound? So go ahead and type in your answers in the chat. And while you're doing that, I also want you to try a couple of experiments with me at home, right? So the first thing I want you guys to do is to take your fingers, put them up to your throat like that, and say, ah. Go ahead, type in, what did you feel? Now take your fingers, put them on your nose, say, again. Tell me what you feel. And then finally, touch the top of your head and say, ing, ing, ing. What did you feel? You should have felt vibrations. Sound is a vibration, and it is also a wave. It's a very special type of wave known as a compression wave. So sound is a physical wave. That means that it needs something to travel through. It needs a medium, solid plasma. Now, if we were in space and I were talking to you, would you be able to hear me? No, absolutely not. The vacuum of space doesn't have any matter between it. So though you would still produce a vibration in your throat, that sound would not travel to my ear. So I want to go ahead and pull out our first slide so we can talk about the nature of these waves. We also call it a transverse wave. Now, this is a really great way to measure sound, and you'll notice there are a couple of words here. So you'll notice that the little hilly things are called crests, and the space between them is the wavelength. We'll talk about what wavelength is in a second. And then little hills at the bottom are the trough. When the crests and troughs are a little bit closer together, that is a high wavelength. They're farther apart, it's a low wavelength. Pretty simple, right? Now you'll also notice there's a line in the middle of that first crest that says amplitude. Well, the higher it is, the louder that sound is. The lower it is, well, the more quiet the sound is, right? So I want to go ahead and show you what a compression wave looks like, and then we'll go back to see how this looks like. So I brought a giant slinky today, and if you have a slinky, you can always try this at home, right? I'm going to go ahead and stretch it, and I'm going to let go of this side. I want you to make some observations. So you notice that that wave goes to my left, right? But what else happens? Well, that wave comes back to me. What is happening there? Well, when it comes back to me, that's the echo. No pun intended. So have you ever been inside of a giant room, maybe a hall, maybe even a cave, and then you hear your name, back in your ears, that's the echo, and that's exactly how that works. As for waveling up this giant spring, and this will be able to kind of do that transfer. So I'm going to start off slowly. Right now, you should see two crests and troves, right? So relatively low wavelength. I'm going to go a little faster. Now you should see three. We have a higher wavelength, right? Pretty cool stuff. But why is this important? How can we manipulate that? Well, as Anna mentioned, I am a musician. I play a few instruments, and this is one of my favorite violins. And this is actually a really great way to manipulate sound. So you'll notice we have different types of strings. Let me zoom in a little bit closer so you can see. There we go. Some of these strings are thicker than others. Have more space to travel through. The notes are going to be much lower. So go ahead and listen. Okay, relatively low note as compared to this string. It's super duper thin. Check this out. So what's the fundamental difference? Basically, this note is much, much lower. This note is much, much higher. The compression wave has less space to travel through here than over here. But here's another way that we can manipulate that sound. What if we took a look at the fingerboard here, we looked at the nut and the bridge, and we see the size of our string. That's all we have to work with. And let's say that I'm plucking the bigger string, right? What if I wanted to make this string shorter? What's going to happen if I do that? Well, much like we talked about, it's going to have less space to travel through, so that note should be higher in pitch. So the string is only that big at that point, rather than having all of that. Really cool stuff. So you manipulate sound in two different ways. One of them we already talked about, amplitude, that is the volume, and the other one we just discussed. Now, what tells you that a violin is a violin and a trumpet is a trumpet, even if you play the same note? Well, that's what we call timbre. That is the quality of a sound. Super cool stuff. If you want me to play this a little bit later, let me know. Let's talk about science. I'm going to put this away for now.
Hey, Raul, could I ask a question?
Okay. Yeah,
All right. So
absolutely.
We've got a couple comments and questions coming in through Facebook. What I think we might need to have you do is we're getting a little bit of a glitch going on. It's moving a little bit slower than you're talking. So what I think we're going to have you do is, would you mind signing off the meeting, rejoining the meeting, and let's see if that fixes anything at all. If not, we'll work through it. We might just need to have you demonstrate things a little more slowly so that there's a little bit less quick motion on the camera. So I'm going to start paging through some questions here. We'll have you sign off, sign back on, and we'll see you back here in just a moment. All right, everyone. We do see lots of your questions coming in. Thank you so much for giving us the heads up. We apologize. I know that a lot of people are having some connectivity issues at home today. Could be something to do with the weather, could not be. So we'll have Raul pop back on in just a moment. But I did see some great questions coming in already. So someone did ask the question that Raul talked about a little bit. And someone asked about how sound travels through space. And the answer was, it doesn't, right? So sound can't travel through space because, as Raul said, it has to move as a vibration. And if there are no molecules like air or solids like this table, right, there's no medium for those compression waves to travel through. And thus we wouldn't have sound traveling through space. So the answer is yes, noise does need to reflect off of something, right? Most specifically, if we're calling it noise, that means that it must be reflecting off your eardrums. That means that you're hearing it. All right, Raul, you look a little bit better already. Could we maybe back up just a little? Could you try the spring demonstration again one more time for us? Maybe go a little bit more slowly and just show that spring demonstration one more time. If not, we can always move on to the slide because I know you've got a couple more photos to show off as well.
Yeah. So I'm going to start off really slowly. This is going to be a low wavelength. So right now we only have one crest, one trough. A little bit faster. We have two now. Even faster. Now we have 3. I don't know if the camera can pick that up. Even faster. We get like 3 or 4 or 5. If I had another person, it would be a lot easier. So that's how you can kind of measure wavelength.
All right, so that's something that people could probably pretty easily recreate at home, right? So if you have a rope
Exactly.
or a string or something, you can try to make a few waves, maybe start with 2 waves like Raul did, and talk about the difference between frequency, and then you can increase the frequency, right, by trying to make even more waves. Very, very cool. All right, Raul, I'll let you take it back away.
Okay, so we measure sound using hertz, which just means 1 vibration per second and kilohertz. And when we make some waves clash together, they either cancel out or help each other out. And that's actually my next slide, if you want to go ahead and pull that up. So on the left, my left at least, you have constructive interference. So you'll notice on that first wave and that second wave, the crests and troughs, they're exactly the same. Amplitude is much higher, right? On the right, we have destructive interference. You'll notice that the crests and troughs are completely different, so they cancel each other out at the end. Using this property, we can do something really awesome with this plate that I have in front of me. So let's try this out. So this is what's known as a Chladni plate. This is just sand. I'm going to go ahead and sprinkle some sand in here, then we're going to get a little bit closer. And we're going to make some waves on here. That's enough. Oh yeah.
All right, Raul, we can
Let's
see
go
it.
ahead and turn on. Perfect.
So we
Okay,
can
go
see
ahead and
it.
turn on my machine. You
But
can
make
see
sure
it?
after you turn it on, Raul, make sure you leave it in place for a couple moments so that we can actually see what's going on before you change anything.
You got it. All right, so I'm going to go ahead and turn my little machine up here to 2.14 kilohertz. This is going to be a little high, so if you don't like high noises, go ahead and lower your volume or cover your ears to feel more comfortable. All right, ready? 1, 2, 3, here goes. Hopefully you can see that. Let me know if you want me to zoom in a little bit closer.
Yeah, we can. Yeah, zoom in just a little bit, Raul, and let's leave it there for just a moment, and we'll let Facebook catch up. And then I know you've got another plan to show as well, but that looks awesome.
Yes. All right. So we now have this super duper cool pattern here, and you'll notice these lines are where those waves help each other out, right? That's our constructive interference. These dark spots are destructive interference, so nothing was formed there. And based on how many kilohertz you put into this machine, you can get some really cool shapes here. Really, really fun. Now, I have another really cool activity here. I'm going to go ahead and zoom out, if that's okay. If anyone has any questions before I go to that, I'd like to take some now. What do you think, Anna?
I think that's a great idea. So if you do have any questions, go ahead and send them in the chat. Raul, I think Facebook took a moment to catch back up. Would you mind zooming back down on the plate just while we wait for some questions to come in? And hopefully people on Facebook can see a little bit better, because I think Zoom caught it just fine. I think we did have a glitch going to Facebook, but maybe you could, while we wait for those questions come in, you could just point out one more time
Yeah.
why the plate looks that way.
Sure. Let's go ahead and restart it so they see the effect. All right. Ready, Facebook? Let me go ahead and reconnect this. And we're going to go up to 2.14 kilohertz. All right. High noise in 1, 2, 3. So for Facebook, you'll notice really cool design here now, right? These lines are where we see the constructive interference. Those waves came in a beautiful shape. And all of these dark spots are where we had our destructive interference. Nothing was formed there. So my next experiment is actually going to be very similar to this, but we're going to take it up a notch. We're going to be using Oobleck that I made before the show. So I'm going to go ahead and zoom out, if that's okay with you, Anna.
Yeah, go ahead.
Okay, cool. Perfect. So let's connect our other machine here. It's the same sine wave generator, but this time it's going to be connected to that speaker. Go ahead and zoom in there. There we go. So before the show started, I made some oobleck. Oobleck is basically just water and cornstarch. You can make this at home. In the comments, if you want me to make a video on how to make oobleck, I am more than happy to do that. But oobleck is a non-Newtonian fluid. So basically, this is going to act as a liquid if I don't add any pressure to it, and as a solid when I do add some pressure. When I go ahead and put that into my speaker cone, you're going to see something super cool. All right, I'm not going to give it away. So let's go ahead, turn our machine on. Let's do. And in goes our oobleck.
Oh, wow. You can really see the vibrations there. It is a little glitchy, but we can see that that fluid is actually bouncing up and down on the speaker.
So some people like to call this an oobleck monster, if you guys check that out later. Much like our last little experiment, now we're making all this oobleck kind of turn like a solid. I can actually push a little bit. It stays solid because of that.
All right, Raul, I think we've actually lost our video feed to Facebook with you. Oh, it looks like it's coming and going. Do you think we could stop and take some questions that people have?
I think that's a good idea. Let's try that.
All right. So someone asked, what makes your voice vibrate?
What makes your voice vibrate? Very good question. So inside of your throat, we have what are called vocal cords. And let me get this out really quick. So you are together like that, all right? So whenever you push air out of your vocal, they kind of vibrate like that. It's much like having two strings together, and that causes a vibration in here, right? That vibration travels through your neck, up into your head, into your chest, and it uses your entire body as a resonating chamber. So kind of like the violin, actually. This violin, it's hollow. There's nothing in there. And that's super good because this may vibrate really, really loudly. Your body's doing the exact same thing. Really cool stuff. Let me get another question. Great question.
Sure. So we're getting a couple requests. People are asking, can you make us a video on how to make oobleck? So in case they want to try it at home.
I promise you I will.
Awesome. Now, follow-up question for me. Should people dump oobleck on their own speakers at home, or is there something special about that one?
Please don't do that. Your speakers are probably paper cones, so that's going to destroy your speaker. I believe Anna put some waterproof spray on this, right?
Yeah, we actually sprayed it with a hydrophobic
This is going to be
coating.
fun. See, that just means it's scared of water, guys. So yeah, don't do that at home unless you have your parents' permission, right?
Yes, exactly.
Good question.
Someone else asked, how is that related to slime? How does oobleck relate to slime?
how is it related to slime? So slime, at least the borax solution in glue one, is also a non-Newtonian fluid. When you add pressure to it, it acts like a solid. You release that pressure, it acts like a liquid. This one is just made out of something else, but it works very similarly to it. I encourage you guys to try this at home. This one's actually super fun.
So someone asked, could we explain one more time the sand on the plate? So maybe don't start it over, but I'm going to pull back up that slide that you shared about constructive and deconstructive interference. Could you talk a little bit more about how that picture, that graph, relates to where there's sand and where there's not sand on that plate?
Sure. All right. Okay. So on the left, you have constructive interference. You see wave number 1 and wave number 2 are identical. When those waves hit each other, they help each other out. So they make an even higher amplitude wave. Destructive interference is the opposite. You'll notice wave number 1 and wave number 2 are completely different. In fact, the crests and troughs are actually like polar opposites. So when they come together, well, they become neutral. There is no more wave there. So the way that that relates to this plate is that these little lines that you see here made out of the sand, you can see that, that's where you have the constructive interference. The dark spots, well, you don't have anything formed there. That's the destructive interference. And again, by changing the different sounds, you can get some really cool patterns on here. Good question.
Very cool. All right, I think we are just about out of questions. If you do have any final questions, please share them in the chat with us. Raul definitely can answer a couple more if you've got them. At this time, as always, we'll take a moment to thank the generous sponsors of the Michigan Science Center. They allow us to bring these programs to you at home every single weekday at 2:30 p.m. Eastern. We're very thankful for our sponsors like Denso and DTE, who keep funding the Science Center even while we're closed because they want to keep the science learning going at home. So big thank you to all of our donors, even the individual donors, people like you who are making donations to the Michigan Science Center as well. We're still keeping an eye out for those questions, so keep typing them in the chat. Thank you everyone for joining. Make sure that you are, as always, liking and following the Michigan Science Center's Facebook page if you'd like to be alerted when we go live every weekday. And if you're looking for any example activities, maybe even some sound activities to follow up after Echo Live, visit our website. So the website is written right here on the bottom of this slide. You can also search on our website for At Home Science. We'll teach you how to make musical instruments. Raul can help us out, maybe create a video for how you could make your own oobleck. Even though you shouldn't put it on your speakers at home, oobleck is a super fun activity, and we can list that on our website as well. So let's see if we have any questions here. Raul, we're getting lots of requests for space questions. Maybe that's not necessarily the theme of today's program, but what do you think about coming back for another space program? Do you think you're up for that?
Yeah, absolutely. I mean, if you think about it, sound is physics, and physics is the study of everything, including space, right? Astrophysics. So yeah, we'll definitely do another one.
So some people ask, where do the waves come from? Do we just make them?
Good question. So if you think about it, waves are just manifestations of energy, right? Energy is what makes matter or stuff move, right? So I right now have energy just sitting here. I have potential energy. When I move my hands, I have kinetic energy. I am transferring that energy here, and that makes a sound, right? So it's all just how matter interacts with energy. Good question. That's where it comes
from. I'm so glad you pulled out your violin because we have a question relating to that. And it said,
sure.
Why are human voices different, but all violins sound the same?
Ooh, okay. So all violins do not sound the same, believe it or not. So my violin is made out of maple, and it was made by hand. Whereas a violin that you might see at school, it's probably made out of plywood, and it's probably made in a factory. So the way that those waves travel inside of that instrument will make that violin sound completely different. The same thing with human voices. Just like everything else, every single human is different. The size and the texture and how much air comes out of us, it's all completely different. So the timbre of voices, the timbre of instruments, and the timbre of just anything is completely unique.
Very interesting. So just like people's voices, violins are unique as well. So we're just about out of time, but I'd like to end it with one final request from the Facebook audience. You may not have your bow, but could you play us something really quick on your violin, maybe just a scale even?
Sure, let's see.
Give the people what they want, Raul.
It's kind of tight in here, so it's very hard to play. Let's see. All right, ready? Hold on. Something like that. It's hard to play where I'm sitting.
That sounded fantastic, Raul. Thank you so much for joining us, and thank you for accommodating Facebook's request. Raul is an amazing musician, and he doesn't just play the violin, so maybe we'll have him back another time and he can show us something else. So thank you everyone for joining. We hope we'll see you back here tomorrow for another episode of Echo Live. Thank you so much, Raul. We'll see you next time.
Thank you. See ya.